Hey, it's Stereo Police. Back with another, what should be a fairly short video. I'm not going to begin the construction process. It's Friday, August 24th. Tomorrow's my dad's birthday, so I'm taking him out of town. I'm going to go visit some old friends and have a little party for him, and I won't be back to work on this until at the earliest Sunday. But nevertheless, I wanted to make a fairly short video about the instruction manual and about the design of the amplifier, I suppose. Just quickly go over the schematics and what you get in the instruction manual, and this is sort of a precursor to beginning the process. So, I did print out the manual. I realized I could bring my tablet computer in here and look at it as I go, but I like to make marks and notes pen and paper style. So I think it's best to print it out, plus the easier for me to read with my need for close-up glasses. But the manual itself, printed out from the website, is 52 pages, so it will kill a tree to print it out, but I really think a hard copy is the way to go. The manual itself is very, very well laid out. Looking at the table of contents, everything proceeds in chronological order. We start out with about the manual, who should attempt the project, the tools you'll need, safety notes. Then we get into the building, the construction process, beginning with the power supplies. Then we move on to the assembling the amplifier circuit boards. Then we move on to some wiring. And then we get to our testing of the power supply. Final amplifier wiring, then testing the whole thing, power off test, power on test, then we install the top. And then we're finished. Sounds so easy, right? And then using it, and then the amplifier goes on with some specifications, schematics, theory of operation, and then table of figures. So very, very well laid out manual. It's nice that they have this section on the theory of operation. This is just a table of figures, and then it begins. So nicely laid out manual. There are some drawings along the way, very helpful. Tables, helps you pick out the resistors and we'll get into that. And get to the building the ground lifter circuit. With wiring. And there's the transformer. I'm just skipping way ahead here. And then we get to the specifications and schematics. And again, about the specifications, the amp is roughly 60 watts channel into an 8 ohm load, and roughly 100 watts per channel into a 4 ohm load. Says we have a small signal bandwidth of 5 Hz to 50 kilohertz. That's a small signal bandwidth, not a power bandwidth. I'd much rather see a power bandwidth here. The frequency response at full power, which is probably not, well, this is 5 Hz to 50 kilohertz. If we have any slew rate limiting, it might be a little less than 50 kilohertz. Everything looks good. Damping factor at 1 kilohertz is over 80. That's perfectly sufficient. Harmonic distortion is low. Intermodulation distortion low. And so on and so on. So the specs are typical of a modern transistor amplifier. This is the schematic of the power supply. And this is the schematic of the amplifier boards. And here is an overall block diagram. Now, I was going to get into some detail about some of these circuits, and I had prepared some notes, but you know, I spent some time going through the schematics, trying to figure out how things operate and work, and I got pretty far with that. I always like to do that for my own enjoyment, I suppose, and also it's nice to know how things work in case you need to troubleshoot. But the way this kit is laid out, I don't know if I don't think it's going to help anyone if I go through that sort of thing. If you follow the instructions, build the boards right, get the proper components where they need to be, you know, barring some rare problem, it's going to work. You know, it's just follow the instructions. Pick out the proper components. Put them where they need to be. Solder properly, no cold solder joints, no components left behind, that sort of thing. It's going to work. So I don't think I need to get into detail into the schematics, but very briefly, the overall construction and layout of this amplifier, the overall on a modular level, you know, we have our transformer, have our power switch, that's our plug that goes into the wall, our power switch, our transformer, primary, secondary, goes into a bridge rectifier, so we have our AC current coming in. Out of our bridge we have our pulsed DC. We go through a filter cap that's going to smooth out the pulses and make a little bit of ripple. And then this is a regulator right here. And the pass component is on the negative rail. A lot of times you see that pass transistor, in this case a MOSFET, up here on the positive rail, but it works the same either way. So this is a regulator, and this is going to regulate the DC. So this is what comes out of it, our positive and our ground. And it's going to regulate the DC much better than a non-regulated traditional style power supply. And it's also going to get rid of this, to a large degree, get rid of this ripple. And so that's our regulator. Then we have our positive and our ground, and each of these goes to the, you know, our amplifiers. There's our, you know, left channel, and that's our right channel. So positive and ground down here. And we have a kind of a star grounding thing sort of going on where all the main grounds are grounded at a common point. You can see the ground from our power supply gets wired to that point. The speaker lugs, the binding post, the negative on each one gets grounded there, and the incoming signal with its ground follows that same trail to our common grounding point. And normally, in many cases, not all, but many, this common grounding point will also be connected directly to earth ground. You know, the center prong of your plug, that cylindrical looking thing, is earth ground, safety ground. But in this case, this circuit differs from sort of traditional layouts by providing a ground lifting circuit, and that ground lifting circuit is this thing right here. And that ground lifting circuit seeks to prevent or reduce hum and noise introduced by virtue of a ground loop, by burning off that ground loop energy inside of this, in this case, a 24 ohm resistor. So I won't get into detail about that. It's a pretty traditional circuit, safe enough. It only lifts, it still provides a connection to safety ground or earth ground by virtue of these. What this is a rectifier, and all it is is a rectifier but not configured as a rectifier. It's configured as diodes that run in both directions. So this 24 ohm resistor will reduce the current of any noise circulating in the ground loop. These diodes right here are those are your safety diodes, so if there ever is a fault that needs to dump a bunch of current to earth ground, it'll go through these diodes. It can go in either direction. That's why they're bidirectional, whichever way the current needs to go. And that capacitor is just RF high frequencies to short those and ground those to prevent those from circulating. And that's it. So that's the ground lifter circuit. And the other, novelties, so to speak, about this overall circuit is, well, I've mentioned this before, it uses the LM3886, the integrated circuit amplifiers. You don't see that often. And it uses a regulated power supply, which is relatively rare in audio. And, well, they have their benefits and they have their drawbacks. And I was going to go down a whole list of the benefits and drawbacks and get into detail as to why, but I really don't think that the average person watching this series of videos is going to care. And also, as I was studying this, I was getting into really getting into detail about this design, and I kind of got lost in it, and it just kind of occurred to me, you know what, stop with the analysis, because this is a kit, it's enjoyment, like I mentioned before, and let's just get this thing built and listen to it and judge the final product as a whole, and not try to sit here and predict and look at, wow, this has got a drawback and this, and it might lead to that, and it might do this. No, I've always been, I like circuitry and I like analyzing it and figuring out how things work, but ultimately, when I do my listening, I'm about the package as a whole, okay? I'm not one of these audiophiles that, and like I mentioned in many of my videos, I don't know all that really cool terminology about how to describe sound, and does it do this and does it do that, and depth and soundstage and pinpoint this, and I listen to the sound as a whole, and I judge it by that. I can't describe it. It's kind of like going to an art gallery. I look at the picture, I look at the painting, Starry Night or whatever, The Scream, and I kind of just, what's the overall impression? What does it do for me? What does it do? What's the emotion of the whole thing? Rather than looking at the individual brush strokes. I can't do that. Meaningless to me. So I got off on a tangent, but the point is, I'm not going to get in. I'm going to wait. I'm not going to sit here and predict or judge based on the fact that we have an IC or the fact that we have a regulated power supply. And there are some serious drawbacks to regulated power supplies. But just real quick, unregulated power supplies, your traditional split rail supplies or even a single rail supply with nothing more than a transformer, a rectifier, and a capacitor or two, they're much better in transients. And they have their output impedance is relatively steady over the frequency range. These regulated supplies, they vastly get rid of the ripple, and they reduce noise, and they provide a nice constant voltage. Okay, a non-regulated supply, the voltage of the DC might vary if the mains voltage goes up or down, or it varies as the load increases or decreases. This is a nice steady voltage. It doesn't matter what the mains voltage is to a degree, and it doesn't matter how much current is being drawn or not drawn from the load. It's going to provide that nice steady voltage. That's great. Doesn't modulate the rails. Doesn't modulate the rails as much. On the other hand, this provides a nice low impedance at low frequencies, but the impedance of this increases at high frequencies, which could lead to instability problems. I could actually plot that out on impedance paper. It's pretty cool. But again, if this thing is designed right, if it's designed properly and tested and there's no instability, then there's not going to be any instability. So again, I'm going to wait and judge the overall product when I'm finished. But I want to tangent, but that's kind of the unique things. It's unusual to see a ground lifter, it's unusual to see ICs, and unusual to see regulated. Not that it doesn't exist here and there, but it's unusual to see it as an overall package. So I'm looking forward to building it and listening to it. So, by the way, power supply, traditional. This is a very. It might look scary, but it's a traditional regulated power supply with a reference voltage, an error amp. Takes a tap off a voltage divider, compares it to the reference voltage, and when this voltage sags or increases, it'll change the current. It's a current source here, and it'll control the gate of this MOSFET to either increase current or decrease current. Just to give you an example, let's say the load here increases, drawing more current and sagging this voltage. This voltage at this voltage divider will go down. If this goes down, it'll increase the current here, and it's going to raise the voltage here, and raising the voltage here increases the current there. Okay, you get the idea. It's a feedback loop. By increasing the current through here, it increases the current through the load, and which brings the voltage back up. It's a whole process. Traditional, standard kind of regulated power supply. And this right here is the pass transistor, the control transistor, the modulated transistor. This is the error amp. These things just control turn-ons and maximum currents. Here is this is the integrated circuit. It's an op amp basically, and if you're familiar with traditional op amps, it's got a feedback loop right there. This stuff right here controls the relay that turns on after a certain period of time to connect to your speakers. This right here comes up with a reference voltage because this is a single supply. Normally these op amps like a split supply where you have a positive and a negative voltage. Well, this operates from ground to positive, so you need to bias it halfway in between. We got this bias here. This transistor comes down from the 36 volts, meets it halfway, but then we have this 36 volts DC appearing right here, and we don't want that to go to the speaker, so we have this blocking capacitor, this AC coupling capacitor that only allows AC through. That's the audio signal to come out to your speakers. Speaker's going to be out here, right? So we need that similar to the blocking or AC pass transistor you'd have in a Class A amplifier. And then you have this little doohickey right here, which is on some amps, not on some amps, and it just decouples. It decouples the amplifier from the load. On the off chance you have these massively long speaker cables and a lot of capacitance in them, you end up getting a capacitive load out here, which could create a series resonant circuit way out there past the audio band. So in that area where you could possibly have resonance, which could be fed back into the amplifier in a constructive manner, which could cause oscillations and the whole thing, you've got this 10 ohm resistor, and this 10 ohm resistor damps that resonance, destroys the Q of that resonant point. But you say, hey, well, I don't want a 10 ohm resistor in series with my 8 ohm speaker. My God, what are you doing? Well, guess what? In the audio band, you have this bypass inductor right here, which is essentially a wire. Inductor at very low frequencies is, in essence, you can consider it a short circuit. So it shorts out this resistor in the audio frequencies, but an inductor, when you get up to much higher frequencies, 100K radio frequencies, all of a sudden this becomes a massive reactance, which then the resistor dominates. When you have a massive, if I've got a mega ohm, I'm making that up, in parallel with 10 ohms, the overall resistance is going to be 10 ohms. But at audio frequencies, if I've got let's call it 0 ohms in parallel with 10, at audio frequencies it's 0 ohms. So that's just something that they call it decoupling, but it's just something that controls resonance outside of the audio band, which could be possibly fed back into the amplifier and cause instability. Okay, so see that? I got into it way more than I started talking, and then I get carried away. And then back here we have our nice description of the theory of operation. You can read this stuff I did. Our nice little color code. I remember about this. Roy G. Biv, right? Our resistor color codes tells you how to read a resistor. You're going to need to know that. And how to deal with some of the shielded cables, which are really, I don't know how my unsteady hand's going to do this, but, and then we're done. So that is the manual. It looks like again, just from the manual, looking at the layout of it, and so far, I've said it before, I'll say it again, I think this is very well done, and there's a lot of care put into this. It's not amateur by a long shot, it's very professional, and I still am very pleased with the whole process. And I'm looking forward to getting started, and that's probably about the last thing I'm going to say before we actually get started building this step by step. And that'll be the next video. Like I said, I'm going out of town this weekend, but I'm going to start as early as Sunday, perhaps as late as Monday. And we'll see how it goes. Alright, so here we are on a Friday night. I'm a little hyper because I've been drinking coffee all day, trying to stay awake, and had a lot of work to do. Sorry if I'm speaking fast. It's not always the case. But I'm ready for a glass of wine. Gotta settle down. Thanks for watching, and the next set of videos will be action. Building. Have a great weekend. Ciao.